I will begin with a word of prayer. So, Heavenly Father, we thank you for this day. Again, Lord, I thank you for the students. Just ask you to bless this class today and help the students to understand what we cover, Lord. In your name I pray. Amen. Okay, so I know not all of you have had Calculus 3, but I want to talk to you today a little bit about the multivariate Taylor expansion. But don't be scared. I'm really just going to talk about the expansion up to second order. Now, in the notes, I have a derivation of the multivariate Taylor expansion. And if you take advanced calculus with me, it's pretty likely that I'll go through that derivation in there. To summarize what you do, you just use the multivariate chain rule paired with the usual Taylor expansion. And when you do that, you find out that a function from, let's say, Rn to R has expansion at, let's say, x naught. And so here x naught I'm using as a vector, all right? And the expansion looks like this. It's just this. F of x is equal to f of x naught plus, excuse me, the gradient of f at x naught dotted with x minus x naught, and then plus, let's say, q of x naught, well, the q of x minus x. Let's see here if I can come up with the right notation for this. Let's say the Hessian at x naught.
What's the Hessian?
I'm about to define it, I know. It's not the Calc 3 that is making you, I don't know, what's the right notation here? Let's say q. Q sub x naught of x minus x naught as the notation I'll use. Plus dot 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 dot. Where these symbols are about to be specifically, I'll write them out for you. Let's start with the gradient. Nabla f so this is called the gradient of f at x naught. So that is just traditionally a row vector, and it looks like this: partial f, partial x 1, partial f, partial x2, oops, comma, dot 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 dot, partial f, partial xn. So this is a row vector. So when I write gradient of f dot x minus x naught, you know, that's just, we take the dot product, the first with the first, the second with the second, all the way to the nth and add them. I'm saying you take those partial derivatives you evaluate at x naught, that gives us the gradient at x naught. The qx naught, I'd say, is the, in words, I'll put the words up there. This is the Hessian at x naught. So q at x naught, acting on x minus x naught, I would say, is this x minus x naught transpose, all right, times this matrix times x minus x naught. So what I'm telling you is that the Hessian is a quadratic form. It's a quadratic form in x minus x naught. All right? And the entries of the quadratic form have to do with second derivatives. Let's see here. So, let's see here. Partial squared f partial x1 squared. And down here, partial squared f partial xn squared. So you have this, just the second partials on the diagonal. And I regret making this matrix so small. Hey, let me try over here. The matrix for the Hessian. And if you don't mind, I'm going to... I mean, technically, these are evaluated at x naught. All right? I mean, because you have to plug in the point where you're expanding. Remember how that goes in like Calculus 2? We've all had Calculus 2. We all remember Taylor expansions are a local idea. We have to plug in the point we're expanding around, right? But I'm going to suppress that point dependence over here. I'm just going to say the matrix of Q, the Hessian. And so the way it works is you do partial squared, partial f, partial x1 squared for this one. And then like, then you have partial f, partial x1, x2. All right? And then down here you have partial squared f, partial x2, partial x1, partial squared f, partial x2, x2, which we just write x2 squared, partial squared f, partial x1, partial xn, and this goes on. I'll write a really nice summary of this in just a minute. Look, what I'm really saying here is that the matrix of Q has ijth entry given by partial squared f, partial xi, partial xj. And my question to you, well, this is a question for you Calc 3 students. If f is a smooth function, all right, if it has well-defined partial derivatives, would this be a symmetric matrix? Remember, one of the things we learned about partial differentiation is it's commutative, in the sense that if I take the partial derivative with f with respect to the jth coordinate first and the ith coordinate second, well, these are equal. I mean, this is Fubini's theorem, I think. And so that's just QJI. So you see, I could really have written, instead of writing x1, x2, I could have written x1, x2 in everywhere. You know, it's a symmetric matrix. The matrix of the Hessian is symmetric. All right? Now, excuse me, truth be told, there's a mistake in what I have on the board currently. All right? And so do you guys remember what the usual Taylor's theorem looks like? Do you guys remember? What's the Taylor series for a function of one variable? Over n, yeah, over n. So it starts out like that, right? And if we set y equal to that, that's the tangent line centered at x naught, right? Then the best quadratic approximation, we got a half here, right? Or 2 factorial, which is a half. Right? So up to quadratic order, that's the first order. And for pretty much for the same reasons, I'm missing something in my current formula, which is the factorial, yeah, but here the 2 factorial, yeah, we'll just write a half. So that's supposed to be here, half. I'd rather put the half here than actually put it into the Hessian, right? Because it's just easier bookkeeping. If I put the half into the Hessian, then I'm writing half a 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 half a. Yeah, you don't want that. All right, let's look at an example. And I'll make this example really, really easy. F of x, y, z equal to, let's say, x cubed plus y cubed plus z cubed plus 3 times x, y, z. So what's the gradient of f look like? Uh-huh. 3, what'd you say, xz? Okay. 3z cubed plus, what was it, 3xy, did you tell me? Oh, 3z squared. I can't do math. I should warn you. You should all be warned, as you watch me try to say things logically today, that in my previous class, for 10 minutes I labored under the delusion that secant squared plus tangent squared was 1. That is where I am today. So, if you think I made a mistake, odds are very good that I made a mistake. It's the time in the semester where I've got a cold from my kids, so there's that. All right, yeah, blame the kids is exactly right. Let's see here. Is there another way we could look at? Is there another way we could look at the Hessian in terms of the gradient? Like, what is it? Can you see anything here? Well, there's a common. If you look at this, there's a common partial derivative with respect to x1 along the top row, right? So you could repackage the Hessian as partial x1 of the gradient of f. Yeah? You could look at it like that. And then the second is partial x2 of the gradient of f, and so forth. The last would be the partial derivative with respect to xn of the gradient of f, if you're willing to take a partial derivative of a row vector, row by row. So with that in mind, I can construct the matrix of the Hessian here by looking at partial x of the gradient of f stacked over partial y of the gradient of f stacked over partial z of the gradient of f. So if you look at that, if I take the x derivative of this, I get what? (6x plus 0, right? This gives me a 3z, because the partial derivative with respect to x of y squared is 0. Take the x derivative of this, it gives me 3y. Take the y derivative of this, I get 3z. I get 6y. I get 3x. I take the z derivative of the gradient. I get 3y, 3x, 6z. So this is the matrix of the Hessian at an arbitrary x, y, z point. All right. Now you guys, we can center this function wherever you'd like to find the multivariate Taylor series out to second order. What point do you guys want me to center at? The easiest one is 0. 0. It's already done. I mean, if you take a polynomial in powers of the variables not shifted, then that's already the multivariate Taylor expansion. Centering it at 1 would be more interesting. Yeah, let's center it at, and when you say center it at 1, you mean 1, 1, 1? Maybe we should do 1, 2, 3 so we can see the contrast of x, y, and z. Yeah. So, didn't your Calc 2's professor they didn't punk you on the final, like find the Taylor expansion for x squared plus 3x plus 2?
I remember that problem on our final.
Yeah. I usually do that. I mean, it's students. Anyway, uh-oh, and so it begins. X. So x naught, quote unquote, is 1, 2, 3 here. All right. So the gradient of f at 1, 2, 3 is what? Ooh. Oops. Well, I was about to say it's 666, but that would be 111. It's a good thing we didn't do 111. This would be 666. So 8. All right. A suggestion: we put a 3 out front. Let's factor the 3 out. Yeah. That will make our arithmetic easier. 1 plus what? 2 times 3? 7? 4 plus 3? Oh. And oh, I wanted it to be 7, but it's not. Right? Yeah. What is it? 11. No, 7, 11. Not bad. Let's see. So this is, now I'll go back to 21, 21, 33. All right, so there's your gradient at 1, 2, 3. What's the Hessian at 1, 2, 3? Well, the matrix of it, okay? We get what? 6, 9, 6, 6, 12, 3. We get 6, 6, 6. Yeah, 6. Oh, that should be. Oh, that's good. We better. Oh, that was close. It was close. 3. I mean, if we're doing things right, it should be symmetric, right? It should be symmetric because the Hessian is a symmetric. It's a quadratic form. It has a symmetric matrix by our construction. 18. Okay. All right. Yep. And okay, so then f of x, y, z is equal to, oh, what is f of 1, 2, 3? I should also figure that out. What's f of 1, 2, 3? 1 plus 8 plus 27 plus 3 times 1, 2, 3. $54? All right, so here it is. We've got 54 plus, 21, 33, 33 times x minus 1, y minus 2, z minus 3, because we're centered at 1, 2, 3. Okay, so I multiply that out. That gives me the linear piece. And then the quadratic piece, x minus 1, y minus 2, z minus 3, times the 696. There you go. This, if we multiply it out, is the best quadratic approximation to this cubic function near the point 1, 2, 3. And there's a half that I have neglected to write. Thank you. All right. Okay. I hope that makes sense. I mean, I know some of you guys have not had experience partial differentiating before, and so like, That's why if I put this kind of problem on the test, if you haven't had Calculus 3, you're welcome to come ask me how to partial differentiate. That's fine. I'll probably just make it so simple that you won't need to ask, because really we were partial differentiating already in Calculus 1, right? If you think about it, in Calculus 1 we ask you questions like, find d dx of a squared. And what are you supposed to write down for that? I guess it depends on your calculus book and the preamble, but usually you're supposed to write 0, right? Because a is a constant. You know, or you have d dx of ax, and you're supposed to say, oh, well, that's, well, x squared. It's 2ax, right? But really, if you look at what you're doing, you're differentiating with respect to x holding a constant, right? That's all partial differentiation is you're treating the y and the z as constants with respect to the x differentiation. That's what this partial x means. So, all right. Anyway, enough about that. So what was the other thing? One of the other things we learned in Calculus 1 is min-max theory, right? And if you've had Calculus 3, we also talk about minimization and maximization in Calculus 3. What did we learn in Calculus 3? Where is the local mins and maxes for a function of several variables? It's where the derivative is equal to 0. I tend to agree with that if we understand that the derivative is the what? The gradient. If we think of the gradient as being the derivative, quote unquote. So I would remind you that the characterization is that the gradient of f at x naught, if that's equal to the 0 vector, then x naught is critical point. So we can look at a function of several variables and look for where the gradient 0 to find potential extremal points. All right? Now, of course, if the derivative was not defined, that's also a possibility. But come on, that's too far into the weeds for us here. We're going to assume our functions are smooth. So if they have critical points, then they have to be where the derivatives are all vanishing. For my example, what are the critical points, if any? For my example, is there a critical point for this function? Where is it if there is one? Let me call this example 1, right? Okay, so for example 1, I heard, so let me write it down. We've got x squared plus yz equal to 0. We need y squared plus xz equal to 0. We need z squared plus xy equals to 0. We need all of those conditions for a critical point, right? And you guys pointed out already, so certainly x, y, z equal to 0, 0, 0 is critical point, right? Are there others? See, I think this example is unfortunate in the sense that I'm not sure it actually has any interesting critical points for us. I mean, if we're not finding them, we're not finding them, right? So. I'll leave it as an open question at the moment whether or not that system of equations has other solutions. I don't know right offhand. Negative one? Oh, you got another one? What's that again? Negative 1, negative 1, 1 is it's a contender. Did it work? What's that? And one more for the bottom one?
That would be 2.
Oh, yeah. So what if we put them all minus 1? That doesn't work, right? Hmm. I'm just going to leave it as an open question for the moment, okay? I'm not sure whether or not there are. I mean, it's a hard question, right? Example 2, I'll make one which has nice critical points. If we look at f, and we'll go back to 2 dimensions, f of xy equal to, how about exponential of minus x squared minus 2x plus y squared. So this function, it actually has kind of nice critical point. All right, so the gradient here would be what? E to the minus x squared minus, oh goodness, let's stop writing that. What do you want to call this? U? All right, I was hoping you were going to tell me Pac-Man, but what's partial u partial x then is what? Minus 2x minus 2. Partial u partial y is 2y. So we get e to the u times minus 2x minus 2. Hey, by the chain. This is not a snooze fest. How dare you? How dare you? All right, so here, I'm going to go back to base principles and just point out that this is, and here's the other notation we use in Calc 3, which is nice. This is fxx, this is fxy, this is fxy, this is fyy. That's the other nice notation for partial differentiation. That's fxx means partial squared f partial x squared. If you didn't, I know some of you haven't had the calculus too. So right above, we got what? This is our fx. This is fy in this notation, right? And so what's fx? Take the partial, we get what? We get e to the u times minus 2x minus 2 squared minus 2 and x. So I'm, oh, fine. Let me, it's going to take me a second here. All right, fxx. Partial x of e to the u times minus 2x minus 2. So that is equal to e to the u times minus 2x minus 2 squared. So what I'm doing there is I'm differentiating e to the u. I know that e to the u, when I differentiate it with respect to x, pulls down a minus 2x minus 2. So I've already got one, so that squares it. And then it's a product rule, so I do derivative of this times derivative of that. So this times that. So the product rule, the second term it gives me is a minus, just a plain old minus 2. And I just went ahead and factored the e to the u out because, why not? Fxy, partial y of e to the u minus 2x minus 2 is, I can just pull out the 2x minus 2 out front, and that gives me e to the u times partial u partial y, which is 2y. Fyy, partial y of 2, e to the u times 2y. And so again, I get e to the u times 2y squared plus 2. So let's see here, if I can clean it up, we can factor out e to the u, right? So let's just write e to the u out front. And can you guys simplify this? I mean, I guess we don't need to simplify it, but what would this be? I think it's 4 times x plus 1 squared minus 2. Because, like, I can factor out a 2. I can factor out a minus 2. I square it, it gives me 4. Factoring out a minus 2 gives me x plus 1 inside the parentheses. And like this one, down here I've got 4y squared plus 2. And what about the other, the off diagonal one? This is just what? Minus 2, well, minus 4, let's say. Minus 4. I'll put the y first. And then we've got a x plus 1, yeah? And same thing down here. All right. So I've done all the work that I need to do to set up the quadratic expansion of this function. All right. You guys tell me, what are the critical point or points for this one? Where's the gradient 0 for this function? I heard negative 1, 0. Do you guys agree with that? Minus 1, 0. Let's see, if we put minus 1 into here, that makes this 0, right? And if we put 0 into here, that makes that 0, so we have gradient 0. Great. And in fact, that's the only critical point. There's just one critical point for this function, right? So let's expand function about this critical point. What's that going to give us? It's going to give us f of xy equals to f of minus 1, 0 plus the gradient of f at minus 1, 0 dotted with what? X plus 1 times y. And then, of course, we have 1/2 the quadratic form at this point of x minus 1 comma y, so to speak. I think that's the notation I used. Yeah. Oh, I'm sorry. I did a sub. I'll fix my notation. Q sub minus 1, 0 was the notation I'm using. All right. And then, of course, plus dot, 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 dot. I must write the plus dot, 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 dot. I've been chastising the Calculus 2 class over their failure to write plus dot, dot, dot. How dare they? Some of them. Anyway. Oh, did I say x plus? Yeah, thank you. Okay, so this was very foolish to even write because the gradient is what? 0. So what we're looking at is just f of xy is equal to, what's f of minus 1, 0? That's e to the, oh, wait a minute. What is it? E to the minus 1? Yeah. So that's e to the minus 1, also known as 1 over e, plus 1/2 what? Well, x plus 1 comma y times some 2 by 2 matrix, we'll figure out what it is, times x plus 1y. So what goes in that 2 by 2 matrix? It's we just got to plug in our critical point into the, we figured out that e to the u is what? I'll just pull that out front just to keep it out here, out of our way. E to the u is e to the minus 1, right? U is equal to minus 1 at this point is what we figured out in our previous evaluation. So then what happens when I put in minus 1, 0 into here? Negative 2 and 0, and 0, and 2. So what is this? We've got, 1 over e plus 1 over 2e times what? Minus 2 times x plus 1 squared plus 2 times y squared plus dot, 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 dot. So there you go. This is the best quadratic approximation at the critical point. So my question to you is f of minus 1, 0 a local min or max? Which is it? See, I argue that you can read that directly from the expansion. Because if you think about it, right? If you think about the point, right? Minus 1, 0. This is the critical point, right? If you think about this line versus this line, you'll see that the function behaves rather differently. Along the red line, which is x equal to minus 1, right? We have that f of minus 1y is just equal to 1 over e plus 1 over 2e times 2y squared plus dot, 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 dot. So along this line, it behaves like a constant plus a positive parabola, which if you can envision in your mind, it's going values up and away from the critical point. So it's raising its value along the red line away from the critical point. But along the purple line, we have the local approximation of the function. Well, this purple line is what? Y equals to 0, right? So f of x 0 is just what? It's 1 over e plus 1 over 2e times what? Minus 2 times x plus 1 squared. So what's that? What's that? Well, that's again a parabola, but this time it's opening down, right? So the function's decreasing either direction. So we have it's increasing away from the critical point on the red line. We have it's decreasing along the purple line. So it's increasing one way, decreasing another way. What kind of point is this? In Calculus 3, we learned to call these kinds of points saddle points. So my question is a loaded question. It's neither a min nor a max. In fact, this is a saddle point. It's a critical point, which is not a local extrema. It's a saddle point. The beautiful thing here, guys, is we can, do you guys remember what the second derivative test was in Calculus 3? The big D? Right, yeah. So let's think about this. So we have our Hessian, right? And at some point not of, let's say, h comma k, we let h equal to x minus x naught. We let k equal to y minus y naught for brevity's sake. And so the Hessian can be written as hk times this matrix, right? All right, like this. Now, to be more precise, these are all evaluated at x naught, y naught. So the fundamental observation here is if the gradient of f at x naught, y naught is equal to 0, then f of xy is equal to f of x naught, y naught plus, well, 1/2 Q naught of HK. Because the linear term in the approximation is gone. So what's dominant near the critical point is the Hessian. The Hessian dominates the behavior of the function near the critical point. Things past that in the Taylor expansion, which I haven't even written down today, are like cubic or quartic or quintic. And those are even smaller near the critical point. The only time that things past the Hessian matter for a critical point is if the Hessian happens to vanish. In that case, we need a higher order analysis. But the thing is, this is a what? This is a quadratic form. So I can rewrite this. Right? I can rewrite Q naught of h comma k as equal to, say, lambda 1 h bar squared plus lambda 2 k squared, where, you know, h bar, k bar are, you know, eigencoordinates. I can change coordinates to diagonalize the quadratic form. And so if you think about that, right, what would make it a local min versus a local max in terms of eigenvalues? Let's think about this. Local max, you would want lambda 1 and lambda 2 to both be less than 0. That would say this thing looks like it's like a parabola opening down in both coordinate directions, both eigendirections, which would mean it's like a local maximum. It's the top of a hill if you have both eigenvalues negative. The reason for the minus here is the same as the reason for the minus in calculus 1. It always grates against everyone's intuition on first glance because you're like, minus, but it's supposed to be the max. I know. Max. All right. On the other hand, local min, you would want both eigenvalues to be greater than 0, right? If both eigenvalues are greater than 0, then it's like a parabola in both eigendirections. So it's like a paraboloid that opens up locally. If, on the other hand, you wanted to saddle, you would have lambda 1, lambda 2 less than 0. The product of them less than 0, which means 1 positive, 1 negative, or 1 negative, 1 positive. In either case, locally it's like a hyperboloid, which opens up in one direction and down in another. I told you guys last class that we can characterize the eigenvalues for a 2 by 2 matrix in terms of its trace and determinant, right? What's the trace and determinant of the Hessian matrix? The trace of the Hessian is fxx plus fyy, right? That's the trace of the Hessian. What's the determinant of the Hessian? Determinant of the matrix of Q. It's fxx, fyy. There's no 2, just minus fxy squared. Does this, if you've had calculus 3 and you really remember your stuff, you'd recognize this as quote unquote big D squared, right? I mean, that's the thing we look at for the second derivative test, right? And what does the second derivative test say in calculus 3? It says that if this big D squared is what? How's it go? Remember? If the big D squared is less, or I think we just call it big D, right? There's no square. If the big D is what? Less than 0, and what? Oh yeah, there's no strings attached, right? If big D is less than 0, then, you know, saddle point, right? But if big D is greater than 0, how's it go? You have to, yeah, exactly. We check fxx positive implies local min. fxx negative implies local max. The thing is, guys, if you think about the determinant being positive, all right? Let's see here. Let's see here. Of course, the trace is the sum of the eigenvalues, right? That's something else we know. Can you see why? For a local max, we need lambda 1 and lambda 2 both negative, right? So if you have that the sum of these, that means that the sum of lambda 1 plus lambda 2 is negative. If you think about it, you can't have the possibility that the second derivative is positive, and yet you can't have d positive and the sum of these things. I'm trying to think of those. In this case, the sign of fxx and fyy are inextricably linked. Like if the d is positive, it forces the sign of the second derivative of x to be the same as the sign of the second derivative of y, if you think through it. So like from a linear algebra perspective, a more natural test would be, is fxx plus fyy? Well, to me that's more natural because it's the trace, but literally this second derivative test is nothing more than looking at the eigenvalues and analyzing the quadratic form and its eigencoordinates. Let me give you a bigger picture. So that's as close as I'm going to get to a derivation of the second derivative test in Calc 3 for here. The thing is, now that you know about quadratic forms, right, and how to set this up, you can equally well write down a min-max theorem in higher dimensions with what we know. See, because all you have to do is if you have f from Rn to R, and if you have that the gradient of f at some point is 0, then we can expand f of x as f of x naught plus 1/2 q of x naught times x minus x naught, so to speak. And this is a quadratic form. So this can be rewritten as lambda 1 let's say h1 squared plus lambda 2, I'll do bars, h bar 2 squared plus lambda n h bar n squared. You can make a change of coordinates to make the quadratic form look like that, where those are the eigenvalues, lambda 1 through lambda n of the quadratic form. So if they're all positive, it's a local minimum. If all the eigenvalues are negative, it's a local maximum. If there's a mixture of negative and positive, it's a saddle point. Right? If any one of them 0, further analysis is required. We can't tell, because if it's 0, that means that it's kind of like a trough, and then the cubic and higher order corrections can manipulate it to become one way or the other. We can't really say for sure if it's a saddle or a local min-max. If there's a 0 eigenvalues, further analysis is required. But that's the big boy, big girl version of the second derivative test in Calculus 3, which we cannot say in Calculus 3 because, of course, much like Calculus 3 is not a prerequisite for this is not a prerequisite for Calc 3. So that leaves this discussion where? Advanced calculus, that's true, yeah. Which is where I'll have this discussion again. But, yeah. Anyway. So, there you go. I have more systematic discussion of this in the notes, of course, but I hope that helps you understand where I'm coming from with the homework problems which were about this, yeah? So, next time we will talk about the musical morphism and bilinear forms and all that stuff. So.